Observers in special relativity are the scientists. And scientists take data. And the idea is they take data with detectors, like scientific instruments, like voltmeters and rulers and clocks to measure time durations. Things that record how bright light signals are, or how loud noises are, or how hot something becomes, like the temperature, right? So scientists use these detectors. And these are the observers, but in special relativity, the idea of an observer is actually quite careful. So we're going to have a careful description of exactly what's meant by having an observer. So first thing to point out is a point of view observer is what you normally think of when you think of a scientist. So a point of view observer, for example, has a detector somewhere. So let's put a detector. So detectors are symbolized by capital D. And this detector, right? So if you're an observer with a point of view is a single or one point of view. You have one detector, right? And this one detector essentially waits for information, right? So this detector has to wait for information. What I've drawn is maybe a coordinate system, and this detector has a location in the coordinate system. So if something happens, right, for example, let's have a firework, right, like a little M80. So this little firework explodes, right, so this is a little explosion, and this explosion happens at this x coordinate and this y coordinate. So that's the location of the explosion. But this detector is far away from the explosion, and so this detector doesn't get information about the explosion until information gets there, right? You have to wait for information. So there is a time delay, right? And there's a time delay because sound travels at 340 meters per second, for example, and light travels at 3 times 10 to the 8th meters per second, roughly. So there's a time delay. And the mistake that a lot of people make many people make is to say that this is special relativity. So the mistake, this is a mistake, this is not correct. They say that special relativity is because signals can't travel any faster than the speed of light, so there's always a time delays. There's always a detector needs to wait, and that's actually absolutely true, but that's not what special relativity is. Special relativity is more interesting than that. So special relativity is about how to relate the data taken by different observers. And the observers are, so these observers are not point of view observers. So that is special relativity is not necessarily, like, it's not restricted to just worrying about time delays for single observers, or I mean a single detector point of view observers. Okay, so the question is what is an observer in special relativity? So we have to talk about this. So let me show you what one observer looks like when people do special relativity and refer to an observer. So what I'm drawing is a coordinate system, and in this coordinate system here is a special relativity observer. So one special relativity observer has an infinite number of detectors. So the idea is there's a detector everywhere, right? Can you see I'm drawing a detector everywhere? So these detectors, these are all detectors, right? Spread out in this coordinate system. So each of these things is a little detector. And these detectors have no relative motion. Whoops. They have no relative motion. So this detector right here and this detector right here, for example, they are always going to be standing next to each other. They don't have a relative velocity compared with each other. So these detectors have no relative motion. They are stuck in place in their x, y, z coordinate system. And so you imagine these little detectors being stuck to in their positions, right? Sitting there recording data, recording information, physical information like temperature or brightness, or sound level, lots of things, right? And they are stuck in place, kind of like as if there is a rigid frame, right? So this rigid frame of detectors. And so this word right here and this word right here get put together into what's known as the observer frame. So this right here is what's meant by an observer in special relativity. So this observer could be called O, that's the observer's name. So all of these detectors in this coordinate system belong to the scientist O, and O is really smart, and O knows that the speed of light is this. So O knows how to calibrate their frame detectors. So what's meant by this is O knows that adjacent detectors, say, are always 1 centimeter apart, right? So 1 centimeters is, say, the smallest distance of resolution. And also, all of the detectors, so, so distances are known, and also the clocks are all synchronized. That is, even though the detectors could be very far apart, so let's look at these two detectors at opposite corners. The idea is this detector has a clock, and this detector has a clock, and those clocks are synchronized. Not only do they run at the same rate, but they always read the same value at the same time in the frame. So that's a little bit confusing. Like, how would you synchronize clocks? Well, you could say, you know that this detector is a certain distance away on a diagonal, and you know that if when this clock says 0, it takes a certain amount of time such that this clock knows how to synchronize itself just based on the distance and based on, say, the speed of light. They use a light signal to synchronize themselves to each other. I'm not doing a great job explaining this, but the idea is there is a way for all of these clocks to read the same value at the same moment in time. You can, everybody is smart enough to do this. This observer, this scientist is smart enough to figure out how to make that happen. But really the point is this observer frame is a frame of detectors. And in this frame, all of these detectors are operating all the time. They're just listening 100% of the time. That's what's special about an observer frame. Observer frames, they are known as omniscient and omnipresent. So omniscient means all-knowing. And what this means in terms of the technology of an observer frame is detectors can measure any physical data, right? That's the sense in which it knows everything. Also, it's omnipresent. It's everywhere at the same time, all the time. That is, the detectors are everywhere. There's an infinite number of them framed out in the observer's reference frame, and they are always on, and they are always paying attention at the same time. So these detectors record events. And the notion of the event is very special in special relativity. So an event has a space-time coordinate. So it happens at a certain time in the observer frame, and it happens at a certain x, y, and z location. So this right here is a big deal. Okay. So two different observers, right? Special relativity, an observer has an infinite number of detectors, and special relativity is about how to relate data taken by different observers. And the observers are these infinite detector observers. This is one observer frame. The point of special relativity is to relate different observer frames. So the relativity is the relationship between observer frames, different observer frames. So what differentiates observer frames is that two different observer frames have relative motion. So here's an example, and this is typically what you see when you're introduced to special relativity. So the typical example diagram of two observers, two observer frames with relative motion. So what this example looks like is, here is an observer frame whose coordinates are, for example, x, y, and of course z. I'm not drawing it. And x, y has some sort of way to keep track of time durations. So there's a timer at every location in the observer frame, and this thing belongs to O. And there is another frame of reference called called the prime frame of reference. This is observer O prime. So this is O prime. So that's how you say it. So the little apostrophe is O prime. And O prime has a relative speed of u compared to O. That is, O prime moves along the positive x axis at speed u relative to O. And you can switch it around and say that O moves along the negative x prime axis at speed u, right? It moves in the opposite direction, but at the same speed, at the very same speed u, relative to O prime, right? This is the relative motion of two observer frames. So the observer frame O has an infinite framework of detectors, right, that are all reading according to that timer, observer O's timer. But observer O prime also has an infinite number of detectors, but they are all recording information for the scientist O prime. Oh, and I forgot that this also brings along its own timer prime. So there's timer associated with the observer O, and observer O prime has its entire infrastructure. It has everything that O has, but so we have to be cautious because the detectors aren't the same detectors. They operate the same way. They're equally smart. These are equally smart physicists who know how to build things very well. They're good engineers as well. So all of the detectors in O and all of the detectors in O prime, each of these physicists will be able to use their detectors to arrive at the same physics, right? So what's more is these observers, these observer frames, are recording things that happen, events that happen in the same universe. So in the same universe, if a firework goes off, so here is a firework or an event, observer O has a detector that can record the time and the location of that event, But at the very same time, with relative motion, there is a detector D prime that can also record the very same event. So the same event is recorded by O and O prime. O gives some data that the event has the coordinate t, x, y, z, but O prime gives the event a coordinate t prime, x prime, y prime, and z prime. Right? Special relativity is the relationship between this coordinate and this coordinate. This is what special relativity does for us. It's the relationship between space-time events as measured by two different observers that have relative motion. One last comment that I'm going to make is actually I have two comments. So two final comments for this little video. So number one, all the observers, right? So you can call them O, O prime, O double prime, O triple prime, or something like that, some sort of way of labeling the various observers. They are restricted to be inertial observers. And I described what's meant by an inertial observer in a previous video. So what this implies is the relative motion between, let me actually just write the word out. So between observers is unaccelerated and there are no rotations. I'll just stick that in a little bit extra. So none of these frames are allowed to be rotating relative to any of the other frames, because a rotating frame is a non-inertial observing frame. But in particular, if all these are already inertial frames of reference and they have relative motion between them, then the relative motion is unaccelerated. There is no relative acceleration. So that's one of the notes. It's basically, you just are restricted to saying that all of the observers are inertial observers. It doesn't mean that you can't do physics from a non-inertial frame. In fact, actually, satellites, airplanes and satellites and things that move around in space, like back and forth, or with acceleration, in order to understand where they are and how fast they're moving relative to something else, you need to include the fact that they are in an accelerated frame of reference, and people are smart enough to do that. But physics tends to be quite special when you observe it from an inertial reference frame. It tends to be simpler, and it tends to follow Newton's laws of motion in a simple, non-headache kind of a way. So the second note, so you should just assume that when you're being introduced to relativity, the fact that you are being introduced by inertial reference frames is an important sort of data point for your brain to keep track of what you're learning, actually. Okay, so the second point is an interesting, just sort of a thought experiment. And this thought experiment will conceptually, so conceptual help to understand length contraction, which is something that is a typical interesting first sort of result of special relativity, is that not all these observers are going to observe the same lengths of the same thing, even though they all know how to build a meter stick. Okay, so, and those meter sticks, if you know how to compare them, all the meter sticks are the same. They're identical meter sticks. But anyways, here's a thought experiment. How to measure the length of an object while it is moving, right? So let's wonder about that. So here is, for example, an object, and it's moving through space with a velocity v. It's going towards the right. And here is an observer's, so this is the observer O, and this is the observer's ruler, right? So how are you going to measure the length of this object while it's moving? Like, you're not allowed to reach out and grab it and make it stop for a second. It is moving, and you need to figure out how to use your ruler to measure the length of it while it's moving, right? You're trying to be a benign measurement device. So what you'd maybe do is you'd record where is the left-hand side on my x-axis ruler, and where is the right-hand side. And what you'd do is you'd say that the length was the difference between these locations, right? This is the length measured by O while this thing moves. But the careful thing that you need to do is, as an observer, you need to make these measurements at the same time. That is, the moment that you measure the left end, you need to also measure the right end at the same moment in time. If you do them at separate times, then maybe this is the earlier measurement. By the time you make the right side measurement, this object has advanced over, and this is where you'd measure the right hand side. So then you'd measure the length to be too big, right? So this is a big deal, and it's going to help you have a conceptual head start on what's meant by a length contraction.